Today we are going to speak about limit of a function. We'll start with a function which I call y, or say f of x, and I call another function gx, which is x plus 1. Now you will look at it and say, what is this? They are the same. Because from your elementary mathematics, you will just do a factorization of them. Cut them. And you will get this. They are the same. I agree with you. They are the same. Except at one point. This function, there is some problem at one point. So let us see how it works. Let me try to first plot this function. I make a box. I put 0, x equals 0. My gx will be 1, x equals 1, gx will be 2, and so on. And so I will get a straight line something like this. This is 0, this is 1, 2, and so on. And at x equals 0, gx is 1. This function also now I will plot. I'll write x, fx. I'll plot this function. For the timing, I'll run this off. I'll put x equals 0, minus 1, fx equals 1. So this agrees with this point. Then here x is 1, I take that as 1. Oh, that creates a problem. Because once I put x equals 1, this becomes 1 minus 1 by 1 minus 1, which is 0 by 0, and 0 by 0 is not defined. So at x equals 1, this function is not defined. So otherwise I will have a same graph like this, except at x equals 1, where this function will not be defined. There will be a blob. So that's the only difference between these two functions. I don't know the value of this function at x equals 1. So what will I do? First I say, well, I can't plot this function. That's one way of looking at it. And the other way is to say, okay, I can't plot it exactly at 1, but what happens if I take my x towards 1? From the right and from the left. It's something like, you've got this point, and you are walking down this road, and your girlfriend is walking down this road. In this road, you will meet each other. Here, there will be a problem. At this point, there is no road. So both of you will fall into a huge hole. So we can ask the question, how close can you and your girlfriend be towards each other? That's the basic concept of limit. As x tends to 1, we write this as limit. As x tends to 1, what is the value of this function fx? Now, as x tends to 1, but not equal to 1, not equal to 1, then my this form x minus 1 is not 0. Suppose if it tends to 1 from the right hand side, say x is equal to 1.00001, then x minus 1 is a small number, but it's not 0. Suppose it comes from the left. So if I say x is equal to 0.999999, then also that minus 1 is a negative number, but they are not 0. And if they are not 0, then only you can cancel, because otherwise you know very well you cannot cancel these two and get 1. This is rubbish. So in order to avoid that, we take points very close to 1. From the right we take a very close to 1, left very close to 1. But as long as I am not touching that point, I am through. Now once that is taken care of, the huge hole is being taken care of, I am avoiding that hole. Now I can just put the value, and that is 2. So we say limit of this function as x tends to 1 is 2, but if at 1 is not defined, that is the main motivation behind understanding limits of certain functions. Okay, now we will try to extend this for some other functions which are slightly higher order. Let me say x cube minus 1. By long division or by factorization, you know that this is equal to x minus 1 into x square plus x plus 1 by x minus 1. So as long as x is not touching 1, then I can say limit of fx is as x tends to 1 is 3. 1 plus 1 plus 1. So again, if I plot this graph, first for my fx to be x cube minus 1 by x minus 1, and then for my gx, which is x square plus x plus 1, I'll see, I plot the function. I put x equals 0. My fx will be, or my gx will be 1. And if I put any other number, x equals 1, my gx will be 1, 2, 3. So x equals 0, 1, x equals 1, 3, and as it is a quadratic function, we will have a parabola like this. This is, as I said, my gx. This is my x. Again, at x equals 1, this is fine for gx, but when I replace gx by fx, which is this, then at x equals 1, there will be a hole. So again, if you and your girlfriend comes, you will never meet, you will fall in the pit. Similarly, you can continue this for the higher order function. I'll just do it for one more, which is x4 minus 1. Again, that will be equal to, if you do the division, you will see that that's equal to x cube plus x square plus x plus 1 when x is not equal to 0. So I will, for the timing, write this as x minus 1 by x minus 1. This is my fx. If I call my gx to be x cube plus x square plus x plus 1, I plot this function. I'll plot gx versus x. At x equals 0, gx is 1. And for x equals minus 1, gx is 0. So it will be a function something like this. I'm sorry, it will not be like this, it will be like this. It will keep increasing, it will keep falling. So again, at x equals 1, gx is perfectly well behaved, but instead if I call fx, then the function is not defined at 1. But if we have to find the limit of fx as x tends to 1, I'll do this as is very close. As I said before, I can cancel these two and I will get 1 cube plus 1 square plus 1 plus 1, which is 4. So we have understood that at x equals 1, this function will have a blob, and so we take the limit and we found the limit to be 4. Now as your homework, I give you a generalized form of this, which is x to the power n minus a to the power n by x minus a. Show that when x is not equal to a, fx is x to the power n minus 1 plus a x to the power n minus 2 plus a square x to the power n minus 3 a to the power n minus 1. Show this and finally prove that the limit of this function fx as x tends to a is nothing else but n a to the power n minus 1. That's all for today.